Yeah, so I hope the screen is visible to you. My slides are visible.
Yes, sir.
Okay,
Yes, sir.
so yeah, so now let us start
Yes, sir.
and let us begin from where we left in the last lecture. So in the last lecture, we had covered, I think we talked about the wafers and then how to calculate the die yield and defects. And then we also talked about the noise in digital ICs, and we talked about this voltage transfer characteristics and noise margin calculations, right? So these were the things we talked about. Yeah, and we also talked about how to locate in the noise margin calculation, how to locate the VOH or maybe VOL or VIL and VIH levels on the VTC, right? So we said that to find out this VIL and VOH, you need to locate a point on the VTC where the slope is -1, right? So then you will also find that in many other literatures and many other textbooks, they have given another way to find out these VIH, VIL, VOL, and VOH levels. Right? So let us discuss that approach also to how to find out or locate these levels, that is VIH, VIL, VOL, and VOH for noise margin calculations. So for the noise margin calculation, we locate these points on our VTC. Let me draw the VTC quickly once again. So we draw this VTC, let us say. So this kind of VTC we had seen. Okay. So this was our VTC earlier. That is voltage transfer characteristics of the inverter, where on the y-axis you had V out, and on the x-axis you had V in. Okay. And we said that because of this levels, that is the output levels, that is VOH. Yeah. So the VOH largely depends upon the gain of the inverter. Yeah. So whatever inverter you are using, we'll know later that these levels, that is VIL, VOH, or VIH. So these depends on the gain of the circuit. So for example, in this case, we have an inverter. So the gain of this inverter will decide these levels. Okay. And let us say my VDD lies somewhere over here. Okay. And my VOH and all these levels can be found by either this approach, where you find a point on VTC where slope is -1. Okay. So this technique we had already seen. Now let us talk about the other technique by which these points can be located on VTC. Okay. So for that, let us draw this VTC once again. Okay. And we also draw the inverse of this VTC. Okay. So let me draw the inverse of this VTC. This is similar to what we had seen earlier. Okay. So this is the invert of this VTC. Let's say this is the VTC of my inverter. And this one is the inverse VTC of the same inverter. So the other method says that you need to draw a rectangle in this area, okay? The largest possible rectangle in this area. So maybe let's say I start from here maybe. So I draw a largest possible rectangle in this area. Maybe let's say this is my largest possible rectangle if. Okay. And then we select these 2 points, yeah, where this rectangle is touching the 2 VTCs. Now on this point, let us extend these 2 points, and the points where it cuts the V out and V in or Y and X axis. So that becomes so this point becomes my VOH, and this point becomes my VIL, right? Now, as I said, that this VOH and VIL levels, they depend largely on the gain of the CMOS inverter. But by this approach, we say that we try to draw a rectangle here in this portion, and the rectangle should be the largest possible rectangle. Though it is very hard to draw manually the largest possible rectangle. Okay, but yes, some simulation tools, they also utilize this approach where they use some algorithms to generate the largest possible rectangle here in this area. So VIL and VOH can be located. Okay. Now for getting this VOL and VIH, so let me draw this inverse characteristics once again here. So I'll draw this inverse transistor CMOS inverter characteristics once again here. So I'll draw it here. So let us say this is the same inverse transistor CMOS inverter characteristics. Okay. So for this characteristics, the y-axis is V in. So the axis is also rotated here. So that is how you are able to get this inverter characteristics. So my voice is, I think, audible.
Yes, sir.
Okay.
Yes, sir.
Now
Yes,
we locate the same point here, right? So this was the point here. So the same point we locate here. Maybe let's say that this point is here, right? The largest rectangle where that had cut the invert BTC characteristic. That is this point. The same point. Let's say it lies over here. Now from this point, you'll again mark the points on V out and V in axis here. Okay. Now in this case, this point where it cuts, so this becomes your VIH. Okay. And this point becomes VOL. Okay. Now you will also admit that this VIL.
Can you repeat second graph?
Yeah, can you please repeat?
Second graph, sir.
Second?
Graph.
Yeah, second graph. So second graph is the same here, this one. Okay. That is inverse VTC. This VTC we had, the solid one. And then this is the inverse VTC. That is inverse of this, the solid one. Okay. So inverse VTC of the same previous inverter. Yeah. So this is the dash one, the dash VTC. Let us say that this is VTC number 2, which is inverse VTC. This is VTC number 1, this one. And we have drawn here VTC number 2. Okay. And in this area, we find out the largest possible rectangular block here. Okay. And then wherever it cuts, for example, it cuts VTC or it touches VTC number 2 here at this point. So same point we locate here. And then from this point, we draw these two perpendicular lines on V out and V in. And we say that this point becomes VOL and this point becomes VIH. Right. So this is another way of finding out these points. Okay. Apart from the previous technique where you try to locate the point on this VTC where slope is -1. Right. Now it is sometimes you will see that there are more than one points on the VTC where the slope is -1. Right. So sometimes you will see that on the VTC you will find more than one point where the slope is -1. Now it becomes very difficult to decide which point will correspond to the worst situation, right? So the other method, that is this one, wherein you draw a largest rectangle and then locate these 2 points on the VTC. And for this inverse VTC, you get this VOL and VIH values. Now VIL, so that is also equal to I mean this VIL, this also corresponds to the highest value of logic low. Yeah, that is highest possible logic low or low voltage level that you provide, that will give you a high output, right? So since we want to apply the low logic level should obviously be 0, but because of some noise issues, this low logic level input is not exactly 0, it is something more, right? So how much more? Up to only VIL. That is, this is the highest value of logic low input voltage which can be applied, and for which this value you will get an output which will be high. Okay. So these are the two methods by which you can find out these 4 points and then calculate the noise margins. Okay. Now let us talk about the fan in and fan out issues. Now let's say that this is my driver gate, okay, and this is driving these loads. Okay, so these are the loads to this driver gate. Okay, so the fan in requirement says, fan in and fan out requirement says that the fan in of any gate should be large, and fan out should also be very large. Okay, so fan out large means if fan out is large, you can connect more number of gates here at the output of this inverter. Yeah, if the fan out of this driver gate is large, so that means you can connect more number of loads, that is more number of identical inverters at the output. Okay. Now this fan out, that means this sets the conditions on the input and output impedance. Yeah. So for example, one would say that if the input impedance of the gates which are being driven, for example these gates, okay, so for these gates, if input impedance is high, right, so if the input impedance is high, let's say input impedance is infinity, so the current taken by these, let's say let's go by the same equation, V is IZ, yeah, or I is V by Z, okay. And if I say my input impedance, that is Z, goes high, sorry, yeah, so if I say Z goes high, okay, so the current requirement, that is current drawn, will become low. So if Z goes infinity, so the current requirement becomes 0, that is 0 current will be drawn by the CMOS inverter. Yeah? So for example, these gates, if I say that the input impedance of the gate which is being driven is infinite, okay, so that means the current which it takes, okay, the current it consumes is almost 0. Similarly, if this also has infinite Z, the current which is being consumed is equivalent to 0. Yeah, very minimum current will be consumed. Yeah, and imagine that at the output here, let's say at the output, I have 4 microamperes, or maybe 4 nanoampere, let's say current I have available here at this output. And let us say that the requirement of these inverters is that at least 1 nanoampere will be drawn by each inverter. Okay? Let us say that each inverter draws at least 1 nanoampere. Okay? So how many inverters I can connect? So each has 1 nanoampere input current requirement, that is, it draws at least 1 nanoampere current, and the available current at this output of this gate, that is at the input of all these, is 4 nanoamperes. So obviously I can connect only 4 inverters of this kind. Okay, but if I have my input impedance of these inverters very high, then I can connect more number of output, okay, gates at the output, because the current consumed by these gates are very small. So more number of output gates can be connected here. So that means fan out of my the gate which is being driven, so that should the gate fan out should be large. So for getting fan out large, the gate which is to be driven, so that has to have infinite input impedance. Input impedance should be large enough. Now similarly, if we talk about the fan in, right? So for example here, M represents fan in. Okay, so fan in means the number of inputs or the number of gates that can be connected to a particular gate. Yeah? So number of inputs that can be connected to a particular gate, right? So if the number of inputs are increasing, so that means my circuit is also becoming more complex. Yeah? So this is one of the issues, one of the problems, that if you have a large fan in, the circuit becomes more complex, and also sometimes it becomes very slow and power hungry also, right? Because more input means more complex is the circuit, so that means more number of components or more number of devices are used to make that circuit, right? So that is why there is some limitation on the fan in requirement. So normally you will not see that any logic circuit has more than a fan in of more than 4 or 5. And especially this is a big problem when designing let's say a NOR gate logic, yeah? Because in a NOR gate logic you have PMOSes in the pull-up network, and all those PMOSes are connected in series in an OR gate. So you have a connection of PMOS devices in series, and PMOS are already slow, so the resistance in series which will make them more slow, and then the propagation delays at the output can be affected. So the device, in fact the overall circuit will become slow. So that is why there is a maximum limit on the number of inputs that a gate can have. That is, fan in has some limitation, but fan out, it is always desirable to have a very high fan out. Infinite, it is very good. That is the best situation. Now, based on our discussion, let us say what are the properties, or what could be the properties for the ideal gate. So for an ideal gate,
So fanning, sir, so fanning is low.
so fanning not exactly low, but yes, it should not exceed a limit. That limit is been set to somewhere around 4 or 5 inputs, right?
Okay.
Because more than 4 or 5 inputs, I mean, if the fan in is more, so obviously that means circuit is more complex, the gate is more complex, that is, it has more number of transistors or devices utilized, and especially in the NOR gates where pull-up networks has, as I said, PMOS connected in series. Okay, so more are the PMOS, that is, if the number of inputs are more in the NOR gate, the number of PMOSes connected in series in the pull-up network will be more. So the delay, the TP-LH delay will be more. Okay, so the overall circuit can become more slow and also more power hungry. Okay? So that is why there has been a limit set on fan in. It should not be more than 4 or 5. Right. So for an ideal gate, first of all, we need to have a VTC which should look like this, and then you should have the input impedance. So that should be somewhere around. Input impedance should always be infinity. If it is infinity, it is the best case. And then the output resistance or output impedance should also be 0. Yeah? So imagine if my output impedance is 0 here, yeah? So that is output impedance of this gate is 0 here, right? So again, utilize the same formula here. So if output impedance is 0 here, right? So if output impedance becomes 0, okay, so what happens to the current? Current becomes infinite, right? So that is, if output impedance is 0 here, I have more than 4 nanoampere currents available here, right? So I have more current available here if the output impedance of this gate is 0, right? So that means obviously if I have this thing, then I can conduct more fan out devices, okay? Because my output impedance of this gate is 0. So obviously I have very large current available at the output of this gate. So obviously I can connect more logic gates at the output. So that is why we say that the output impedance should be 0 and input impedance should be infinite, and fan out should be infinite, so that more devices or more gates can be connected at the output, and the high and low noise margins should be equal to VDD by 2, okay? So that it can cover the entire transition region, so that the circuit never fails. Now this is an old time inverter wherein these levels, that is VOH, VIH and VIL, VOL can be located, and then the noise margin can be calculated. So for example, VOH and VOL, they are being located at these points, that is 3.5 volts and 0.45 volts. Similarly, VIH and VIL is also calculated from the same VTC, and VM is also located, that is somewhere around 1.64 volt. So noise margin can be calculated by simply saying VOH minus VIH, that is 3.5 minus 2.35. 3.5 minus 2.35, so that is 1.15 is the noise margin, upper noise margin or high noise margin. Similarly, low noise margin can be calculated by subtracting VIL minus VOL, that is 0.66 minus 0.45, so that comes out to be equal to 0.21 volts. Okay. So this is how the noise margin from the VTC can be calculated. Yeah, but from this, noise margin can also be calculated from the gain of any circuit. Yeah, if I know the gain of my digital circuit, I can calculate these levels. So that calculation part, that is how to calculate the noise margin from the gain of the circuit. So that will be covered when we talk in detail about this CMOS transistor analysis. So we'll talk about a detailed analysis of noise margin also then. Okay. So currently we are only covering the basic things, basic properties of CMOS inverter and basic noise margin calculations. So when we do a in-depth analysis, we'll talk about the dependence of the noise margin of the gain on the gain of the circuit. Now let us also define the delay, okay, or the propagation delay. So propagation delay. So propagation delay of a gate. So that is defined in a way that it is the total time taken by, or the total delay experienced by a circuit when passing an input. Okay. That is, you apply input, the input change, and when the output appears. So after what time the output appears when the input change. So that is actually called propagation delay of the gate. That is the gate delay by the gate, the delay experienced by the gate when passing an input signal. So that is called propagation delay. So for propagation delay, again, we'll come on to the input and output characteristics of the inverter. So here you will find that this represents the input of the inverter. So for the same CMOS inverter, we apply, let's say, this transient input, okay, and on this transient input, you get an output which looks like this. So that is when the input goes from 0 to high, that is low to high, the output transitions from high to low. Similarly, when the input transitions from high to low, the output at the CMOS inverter goes from low to high. Okay. Now, propagation delay is calculated by this analytical expression, that is TPHL plus TPLH by 2. So TPHL is propagation delay when the output goes from high to low. Okay. So remember that we had in a CMOS inverter, we had PMOS here, and then we have an NMOS here, the pull down network. Okay. You apply an input over here, you get an output, some output, and you also have a capacitor here. So this capacitor is continuously charge and discharge. Okay, let's say that this is charge and discharge. So this TPHL and TPLH comes from the charging and discharging of this capacitor. Okay. So this capacitor is, when this capacitor is discharged, okay, so we say that TPHL, that is time taken for by the capacitor to discharge, okay, TPHL. That is getting your output node from high to low. Okay. So TPHL is time taken by this circuit to make this output node go from high to low, or transition from high to low, okay, which is actually through this NMOS you are trying to discharge this capacitor. Similarly, TPLH. So TPLH means you are trying to charge the capacitor via this PMOS up to VDD. Okay. So now this is my TPLH, the time taken by this circuit to charge the output node or charge this capacitor to VDD via PMOS. Right? So TPLH and TPHL, they actually come from charging and discharging of the transistors. Okay. Now, in many cases, you will find that this TPLH and TPHL are not same. So that is why we need to take an average of these two values. Right? Otherwise, if they both are same, one can say that TP is equal to TPLH or TPHL, right? If both are same. But since in many situations you will find that both are not same, so we apply this formula here, that is propagation delay is calculated by the average of these two time, that is charging time and discharging time. Now TPHL can be located from this input and output waveforms. So it is calculated between these 2 points. Yeah, that is these 2 points. So it is calculated at this, between this point and this point of the input and output. That is, you locate 50% point on both the input and output. 50% here means that when the input moves from low to high, and when it reaches 50% of its final value. Final value is VDD. So input is making a transition from low to high, that is 0 to VDD. So whenever it reaches VDD by 2, that is 50% time, you locate this point on the input waveform. Similarly, when the input goes from low to high, output starts moving from high to low. Okay? That is from VDD to 0. So when it reaches again VDD by 2 point, you mark that point here, that is 50% point, and then in between these 2 points, we say that between the time between these 2 points is called TPHL or high to low time, right? Similarly, you locate TPLH, that is when the input is transitioning from high to low and the output is making a transition from low to high. Again, you locate the 50% time points here, 2 points, and TPLH, that is low to high propagation delay, is the time between these two 50% time on the input and output. Okay, when the output is making transition from 0 to VDD. Okay, so 0 to high, that is low to high, output is making a transition from low to high. So I say TPLH, that is propagation delay when the output is going from low to high. Okay, output is in this case going from high to low. So I say propagation delay in high to low, that is time taken by the output to go from high to low. Okay, so this is calculated between the 50% points between the input and output. Okay. So these 2 points you calculate and then find out the time, and then you put these values here, plug in these values here, and find out the propagation delay. So that way the propagation delay can be calculated from the input and output characteristics. Okay. Now, apart from propagation delay, let us also define 2 more things here, and those things are the rise time, okay, and the fall times. Okay. So
excuse me, sir.
Yes, please.
Sir, we did this experiment in lab yesterday. So we were getting, we calculated propagation delay without capacitor and with capacitor. So can you please explain what is the whole difference between, there was a large difference in the propagation delay with capacitor and without capacitor.
Yeah, so obviously, with capacitor, I mean, you added some more capacitor here. So earlier, whatever simulations you had done, maybe some default capacitance was used at the output, and then you added extra capacitance to the output node. So obviously the capacitance, when you add an extra capacitance at the output, so obviously the propagation delay will be large, right? So earlier, the drain diffusion capacitance were already there. Okay. So the tool may have already considered that drain diffusion capacitance, but then you also added extra capacitance. So these are in parallel, so that means they will be add up. Right? So this capacitance also it has to charge now, and the drain diffusion capacitance which is hidden. Okay, so that also it has to charge. So obviously the propagation delay time will be more. Right?
Okay, sir. Thank you.
And in fact, if you connect another inverter here, okay, the same inverter, if you connect here, you will find the propagation delay at this point, it has increased further, because now this capacitance, that is total load capacitance, will also get a contribution from the input gate capacitance of the inverter which is connected, right? So I have, for example, in this CMOS inverter, I also have the capacitance which is appearing at the gate, that is gate capacitance, yeah, at this point, some capacitance. Okay. That is gate capacitance, CG1, let's say, of MOSFET 1 and CG2 of MOSFET 2. So these two also add up and they become part of CL. Yeah? If you add this is inverter, and if you try to add one more inverter at the output, and you try to calculate a propagation delay here at this point, right? So now, apart from this load capacitance which you have already added, you will also have now these two capacitance, CG1 and CG2, which will come from the input gate capacitance of the MOSFET associated with this inverter. So obviously the propagation delay will further go up, no doubt.
Okay.
So, yeah, so let us also define the rise time and fall times. So rise time here means, again, the output is trying to rise from low to high. So whenever the output moves from low to high, that is, a transition is happening. Yeah, please.
Sir, I just want to ask you that this capacitor affects the voltage transfer characteristic of this CMOS inverter.
Yeah, VTC, it can be affected because TPLH and TPHL, so both those times can be different, right?
No, the delay got basically increased, sir, but the voltage transfer characteristic, I am asking about that because, sir, in experiment we have changed that value of capacitance. It didn't change, sir. The curve remains same, sir.
See, ideally, there must not be a much different, because you will see later on when we go on to talk about how this VTC changes with the width of the MOSFETs, right? So you will find that there is not much change. So for example, you will change beta or the W by L ratio of the MOSFET. So obviously, with the change in W by L of the MOSFET, the capacitance values also change, right? So VTC has not much effect of the change of the device sizes or the capacitance associated with the device. It will not change largely, but yes, there is some change. So you will find that VTC shifts from left to right when from here to here. The VTC will shift but that shifting will be very minimum, unnoticeable in many cases, as you might have noticed. That is okay, correct. So that we will read later on when we go on discussing the detailed analysis of CMOS inverter. So we'll talk about these issues, effect of capacitances and the device sizes. We'll talk about them later, definitely. But yes, to this point, you can say that there is a very minimal change in the VTC when the capacitances are. But yes, when the device size, this is W by L ratio, okay, but beta P by beta N. So when this changes, then VTC is largely affected. Okay. So when beta P by beta N, that is W by L of MOSFET P and N, this ratio changes, so the VTC can be affected. Currently, I think you might be plotting symmetrical VTC. So there are cases when the pull-up and pull-down network resistances are not equal. So then the VTC will also be not symmetrical. So VTC will change if the pull-up and pull-down resistances are not same for the MOSFET. So you will see a non-symmetrical VTC instead of symmetrical VTC. Okay, anyhow, these issues we will talk later. Obviously, these are a part of this course, so we'll talk about them obviously later. Now, let us talk about this rise time and fall times, as I said. So rise time is, when the time taken by the input to reach from low to high, right? So we generally say that it is from 10% to 90% we take on this curve, right? So we say that when the input has risen to 10% and when the input has risen to 90%. So between these 2 points, that is 10% to 90%, we say that this is our rise time. So similarly, fall time, that is the time taken by the output to fall from, again, these 2 points we locate. This is 90% point here, okay, and this is 10% point here. So again, fall time is time taken by the output to fall from 90% of the final value to 10%. Okay. Similarly, rise time taken by the output to rise from 10% to 90%. Okay. Now, why 10%? Why not from 0? So because there is very much uncertainty in knowing which is actually the start time. When actually the output starts rising, right? So there is some uncertainty in finding out the exact time, that is exact time when the output starts rising. So that is why, to remove that uncertainty, we say that we select this 10% point and 90% time, yeah, not from 0 to 90 or 0 to 100. Right? Similarly, 50% time, why we select? So there are, I mean, this is just a model and this has been very accurate. In fact, has been seen that you select this 50%. So this is good enough to find out this TPHL and TPLH. Okay. So 10% to 90% here and 50% for TPHL and TPLH calculations. Now, let us come on to this assignment. In fact, you have already done the experiment in your lab. So I hope you are in a position to do this assignment very quickly, right? So in this assignment, you have to find out the propagation delay of your CMOS inverter using this formula, right? That we have discussed. Okay. So here you have to find the propagation delay of an inverter, and that inverter, CMOS inverter, has a PMOS with a width of 15 microns and length of 2.5 microns. And NMOS has a width of 5 microns and length of 2.5 microns. VDD is 5 volts. Yeah, these are all given parameters. And input at the gate. So this is a pulse, and this pulse has following specifications. That is, initial voltage is 0. Peak voltage is 5 volts. Initial delay time is 0. Rise time is 5 nanoseconds. Fall time is 5 nanoseconds. Pulse width and pulse period. Okay. So these are 48 nanoseconds and 120 nanoseconds. Right? So since you have done an experiment in the lab, so this will be a very easy assignment for you. Then you'll have to consider level 2 MOSFET model. Okay. So there are MOSFET models from level 2 to maybe level 50 you will find. Level 1 is also existing, right? So level 1 to 50 MOSFET models are there. So what are these MOSFET models? So let us talk about them also after this slide. So you will have to use this level 2 MOSFET model parameters. And at the output, you will consider a load capacitance of 100 femtofarads. Okay. So once you do the SPICE simulation, I don't know which software you use. So which software in the lab you used? I hope PSpice or CAD?
LT-SPICE.
Yeah, LT-SPICE is also good enough. LT-SPICE, then there are many more softwares. So any of the software you can use, but since you have started using LT-SPICE, it is okay. So you can use LT-SPICE. In fact, in LT-SPICE, you can also edit the model libraries. That is, MOSFET models also you can edit. Okay, in LT-SPICE. So there are many tutorials available on the web on LT-SPICE. You can go through those tutorials. And then you have another few more SPICE based software, that is AIM-SPICE, and then you have PSpice by OrCAD. Okay, so any of these you may download. Okay, PSpice by OrCAD, which is used in Cadence tool. Okay, so this also exists. When student version copies of these you can obtain. And then there is one more open source freeware, right? Open source and full-fledged software. So which is called NG-SPICE. Okay. So any of these you can use to simulate your designs, okay, to find out the propagation delay of this inverter, okay, with these specifications. And maybe you can submit your assignments. Let me change the due date, because this due date is appearing. We used to have the assignment submitted on this date for the previous batch, but for your batch, since we have started late, so today is, let's say, 6th October. So 20th October, let us say, right? So on 20th October, you will submit these assignments to me, say October 20th. Okay. So you will submit the, the VTC, sorry, not VTC, the propagation delay of inverter, that those waveforms you will submit, and then your calculations of propagation delay. Right? So you have to calculate actually the propagation delay here. So you'll calculate the propagation delay from this kind of waveform, that is input and output waveforms. You will locate 50% times and then find out the propagation delay. Okay, and then we'll submit to me on this email ID, that is schoolofvlsid@gmail.com. Okay. Now let us talk about this MOSFET model. That is, here I said that you will be using level 2 MOSFET models. So what are these MOSFET models? So for simulation, obviously you need to have some a model of your device. So whatever device you are using, so that should have some model. So that model is actually used to calculate the device characteristics. For example, you want to calculate current, and that current will obviously be utilized in generating the voltage at the output, okay, or the response at the output of your circuit. So for finding out that current value, your simulator needs some model. So these models are actually also called BSIM models or BSIM device models. And BSIM stands here for Berkeley Short Channel Insulated Gate Field Effect Transistor models. Okay, so these refers to a family of MOSFET transistor models for IC design, and this BSIM model, that is Berkeley model, these are proposed from University of Berkeley, which is present at California, right? So University of California, Berkeley. So this university gives these models, that is BSIM models or MOSFET models or BSIM models, right? And you will also find that there is a group called Compact Model Council. Okay, so Compact Modeling Group or Compact Model Council is again from the same university, University of California, Berkeley. And this Compact Model Council, this actually tries to standardize the use of these models in different simulators, industry-based simulators also, and the academic simulators also. So the job of this is to produce new device models, because with technology, the model should also change, right? So the technology advances, the process technology is advancing, that is the device size is shrinking, the gate length or channel length is shrinking. So obviously the old models, that is the models which were used for large MOSFETs, okay, so those models will not be sufficient enough to predict accurate device characteristics. So you need some other accurate models. So those accurate models, they are being proposed with time, with change in process technology by this group, which is called Compact Model Group, right? So what there are many process parameters, so they always change in the advanced model. Okay, so yeah, so these process parameters must be changed. So for example, in a low length or short channel length MOSFET, the short channel effects have to be modeled by some method. So those high level models, they also include the effect of short channel effect, okay, and many other effects can be added. In fact, they are added. So you will see, I'll share with you the MOSFET models. Yeah, then there are some other models also which are supported by some other councils, that is for example PSP, HICOM and MaxTram. So these are some other councils very similar to Compact Model Council. So they also have given some models for SPICE simulations, models for devices for SPICE simulation. Okay. Now what is level 1 and level 2? I mean, what is the difference between these MOSFET models? So as I said that as you move on to this levels, that is from level 1 to level 50, the complexity of the model increases because the process technology also improves. So the old models will not be able to predict the accurate device behavior. So level 1 and level 2, obviously there are differences. So for example, in level 1 you will find that channel length modulation, that is effect of channel length modulation, that is not considered in level 1. But in higher levels, maybe for level 2, you will find that the effect of channel length modulation is considered. So either you have to provide channel length modulation lambda, or the tool calculates its channel length modulation by some means. So what are those means? I will tell you. Okay. Yeah. So level 1 and level 2, obviously, and the other levels, higher levels, they have differences in terms of accuracy. Higher levels are more accurate for short channel MOSFET. For large channel or long channel MOSFET, these level 1 and 2 are sufficient enough. Now another thing you will notice here between level 1 and 2, that if you use level 2 MOSFET model, you will find that level 2 MOSFET model, the simulation time is more. Okay, so level 1, you will find that run time can be about half that of simulation using level 2 model. So the time it takes to simulate your circuit, so that becomes half if you use level 1 model instead of level 2. But yes, level 1 is not very accurate, level 2 can be more accurate, and it also depends upon the the size of the MOSFET that you are using. So short channel MOSFET, obviously level 1, 2, 3, they will fail. So we'll have to use advanced levels. And for long channel MOSFETs, you can use level 1 and 2, okay, and save some simulation time. Okay. So let us also come on to this assignment. Okay, and this is assignment number 2 here. So you don't have to do much here. Okay. So same inverter which you will simulate in assignment 1. Okay. Now there you had calculated the propagation delay. Now in this assignment you will calculate the noise margin of the same inverter gate. Okay. So the noise margin of the same inverter gate you will calculate. Again, for that you need to plot VTC. From the VTC, you will locate those points where slope is -1, negative, and then find out VIL and VOL and VOH and VIH, 4 points, and then calculate the upper or higher noise margin and lower noise margin. Yeah, same inverter gate, right? And then the second point, what you have to do is that you also have to find out the fan out of the inverter. Okay. So how you will find the fan out of the inverter? You will have to also apply some brain, your own brain. So fan out of the inverter you will find by considering the load inverters are of the same size as the driver inverter. Okay. So apply some mind. Okay. Try to increase the number of loads, that is the same inverters of same size as the driver inverter, and then try to find out the fan out of the inverter. Third thing, you have to also find out the whether the inverter gate has regenerative property or not. Okay, that is the gate in assignment 1, whether it has regenerative property or not. So we have seen regenerative property. Okay, that is after passing through certain number of stages, the output levels are nominal output levels are obtained. Okay, you started off with our input signal which is affected by noise, but after passing, let's say 3, 4 or 5 or whatever number of stages, the output reaches the nominal levels, signal levels, that is full zero and full high. So that is called regenerative property. So for the same inverter, you will find whether it has regenerative property or not. Again, you'll have to apply some brain here, how to find out that whether the gate is regenerative. So just a hint is present here, that is in this case, you will have to find out the number of stages it takes to converge signal to nominal levels in case the input signal is affected by noise. Okay. So what you have to do here is that you just try to connect 4 or 5 inverter gates in series and try to make input of the first inverter. Let's say you want to apply 0, so don't apply 0, instead you apply maybe 1.5 volts or 2 volts. That is, your input is affected by noise. Okay, and then you see that whether the actual 0 level is obtained after passing certain number of stages or not, right? So that is how you will find whether your gate has regenerative property or not. Okay, the fan out of the inverter and the noise margin. Yeah, 3 things you have to find here. Okay, so maybe let us say that the submission date for this one, let us keep the same submission date because this assignment is not different. Okay, let us say 20th October for both these 2 assignments. Yeah, same inverter you have to find out the VTC and then apply the same concepts that we have read so far to find out the noise margin, fan out, and regenerative property or not. So let us say October 28th. So October 20th, yeah, same date, assignment 1 and 2 you will submit. Okay. Now let me also give you a small demo of, in fact you have already done, so there is no point in giving you a demo, but let us, though I used to normally give the demo to my students, so let me open this. This is Top Spice, another software you can use, Top Spice. So here also you can write the same CMOS inverters code. In fact, you can also have a schematic of CMOS inverter and then extract this code, okay, and then change these values. That is, you can change the width and length of the MOSFET, okay, and then whatever transient input pulse you want to use, so that also you can change. Then output capacitance also you can change. All these values you can edit here in this text file, and then you can run simulations. So for example, this is input and output characteristics. So from here I can find out the TPLH and TPHL. Okay. Yeah. So similar to this, maybe let's see what else I have. Yeah. Yeah, so VTC also can be obtained similarly, though you have already obtained, so it will not be a difficult task for you. Okay. Then you can also work on AIM Spice if you wish. So AIM Spice also you can work. So you open IM Spice, you will get a window like this, and then maybe you can.
Sir, excuse me, sir.
Yes, please.
Sir, we
Only
can't see your
PPT is
screen.
visible to us.
Okay. Just a second. Just a second. Sorry, I'll repeat these things once again. So maybe let me share my entire screen to you. Okay. Only PPTs were visible. No issues. Now I think you can see my this desktop, right? So let's say I have a top spice, another spice simulator, so you can also download if you wish. So maybe I have already written the CMOS driver gate, CMOS inverter, right? So for this CMOS inverter, either you can write a spice code like this, or maybe you can simply connect the PMOS and CMOSes and then generate the circuit here. Yeah, and then you can change these MOSFET parameters. Yeah, for example, you can change the width of the MOSFET, length of the MOSFET. As per our assignment, you can change the width and length of the MOSFET, and then you can also change maybe the VDD or maybe the output capacitance. So all these things can be changed, and also the transient response values, the input and output, all things you can change, and then maybe you can run a simulation. So if I run a simulation, I get the input versus output characteristics. The input is here in yellow and output in purple. And then from this input and output, you can locate 50% and 90% and 10% time, and then find out the propagation delays or rise time and fall times. And all these things can be extracted. Then we have another software also, AIM Spice. So if you open the AIM Spice, you will get this kind of window. And in this window, you can start writing your spice code, right? So spice code, you will start writing. How you will write a spice code? Maybe I'll give a small briefing within 5 minutes. I will tell you how to write this spice code. And then once you write this spice code, you can either go for transient response, DC or AC response. So let us say transient response. I click on transient response. I give the step size and final time when the simulation will stop, and I say run. Okay. So in the run, I can also trace whatever input and output I want to trace. So let us say I want to trace the input waveform. Okay, that is transient waveform that I had given. So I say this, and then I run it. So I get the input transient waveform that I supplied. So similarly, the outputs at other nodes in the circuit can also be traced. Yeah? So this is the input transient which I applied. Okay. So similarly, you can achieve. You can perform simulations on any of the software, not just AIM Spice or Top Spice, but LT Spice is also a very good software. So that also you can utilize. Okay. Now let me give you a very small briefing on how to write these spice codes. Yeah? In fact, you will find that I have shared all these information, that is spice tutorial and all. I have shared on my website. Yeah, web page. You go to my web page on a NITKKR website, EC department. So you will find that these informations I have uploaded. Yeah. So this is a brief spice tutorial. So for writing a spice code, let us say we want to write a spice code for this circuit. Okay. So for writing a spice code, first of all, we divide the entire circuit, or we decide the number of nodes here. Yeah? We mark the nodes here. So for example, I mark node number 0 as ground. Yeah? 0 and ground both are reserved values of the nodes names, right? So node name can be either character or numbers. So ground and 0 both are reserved. VDD, ground and 0 both are reserved. So ground and 0 are reserved for ground connections, and VDD is always reserved for VDD connection, right? So let me say that my node number 0 is appearing here. Then between 0 and 1, yeah, this is node number 1. 0 and 1, I have a current source, I bias. And then between 1 and 3, let us say, not 1 and 3, or maybe 0 and 3, one can say. This is node number 3. Between 0 and 3, I have again another voltage source, and between 1 and 3, I have a MOSFET here. So this way you decide the number of nodes in the circuit. Similarly, 6 is my VDD here. So I decide this is 4 number node, this is 7, this is number 2 node. Yeah? I decide the number of nodes here. Okay, I mark it here because these are important. Okay, then we go on to write the SPICE code. So how do I write the SPICE code? So for writing a SPICE code using MOSFETs, I need to provide the model for the MOSFET, which will be used by the simulator to calculate the device characteristics and then the final output. Yeah? So that model is quoted in the file, that is the text file where you write your program. So there you have to include that model file, that is included by using dot model, then name of the MOSFET, whichever is the name of the MOSFET. I mean, this could be anything. Okay, it could be either M1, M2 or anything you can write here. So model, name of the MOSFET, okay, and then type of MOSFET, type of NMOS MOSFET, and then you have process parameters. Whatever are the process parameters for that MOSFET in that level 2 model we are using. So these are the parameters for level 2. So what parameters? For example, threshold voltage, oxide thickness, okay, mobility of electrons. Similarly, gate to source overlap capacitance, gate to drain overlap capacitance, gate to body or gate to bulk overlap capacitance. Okay, and then there are many more parameters. Okay, then junction capacitance, you have parasitic junction in the MOSFET. So the junction parasitics associated. Then junction sidewall capacitance, okay, CJSW, and mutual capacitance between the junction sidewalls. Okay, junction lengths. Okay, so lateral length, so all lateral diffusion length. So all these things are called process parameters, and these can be provided here. Okay, for maybe if I'm using level 2, I'll write level 2 and then level 2 parameters. So where these level 2 parameters you will find these in the MOSFET model file. So where are those model files? I'll share another slide, maybe a PDF with you, that also have uploaded. Let me MOSFET SPICE levels. So this file also I have uploaded on my web page, so you can access. So it has the model parameters for all these levels, yeah, level 1, level up to level 50. Yeah, so if you click level 1, so level 1 model parameters are mentioned over here. Okay, all these model parameters, for example, oxide capacitance, Cox, and the value is also mentioned here. Okay. Then you have intrinsic transconductance parameter, Kp. Then lambda, as I said that in level 1, lambda is not considered. I mean, channel length modulation effect is not considered. So lambda is considered 0 here. Oxide thickness, okay. Then carrier mobility. Yeah, all these parameters are called process parameters. Okay. Then metallurgical junction depth. Okay, all these parameters are called. Since most of these parameters are 0, you will see, because level 1 is not an accurate model, but higher levels you will find that all these parameters have some values. Okay. Then body effect coefficient gamma, so that also is being mentioned here. Okay. Then how to level 1 model equation, that is the current equation, which will calculate current, and then finally based on these current values the voltages are calculated. So what are those model equations? So those also have to be provided in the model files. So level 1 model files, the current is calculated using this formula, right? That is the same formula. ID is mu n Cox W by L VGS minus VT into VDS minus VDS square by 2. So for linear region, you have VDS less than VGS minus VT. So the equation for linear region is this. For saturation region, you have VDS is greater than VGS minus VT. So simply you put VDS is equal to VGS minus VT here, and you will find this equation. That is the equation of current for the MOSFET in saturation region. Yes, all these current equations have to be provided in the MOSFET model libraries. Otherwise, the simulator will not understand how to calculate the current. So you don't have to provide, but yes, these are already there in the simulator. But yes, just for your information, I was telling you how these things work out. Then similarly, channel length effective channel length and effective width, okay, because the gate has an overlap on the channel length. The gate is overlapping the drain and source region, so you need to calculate the effective channel length. Maybe I'll also give you a brief introduction on this device characteristics and device dimensions and device geometry. So then I think you will understand these parameters more well. Then to include this body bias effect, so you have substrate to bulk or source to bulk biases. So these are also being considered to calculate the threshold voltage, yeah? Because threshold voltage depends on this term, and this term requires to know this built-in potential and body effect coefficient phi and VSB, that is source to bulk. Okay, so for source to bulk bias is greater than 0, so you have this equation. Source to bulk bias less than 0, you provide this equation, right? And these things are required because the simulator has to calculate your current based on these values. Okay? So these are called process parameters basically. Okay? Then similarly, if I talk about level 2, it is more advanced model. Okay, so level 2 have some other values of the process process parameters are included, and the current equation is also different, you will see, right? So current equation is little bit more big, so you have included phi here, that is bulk junction potential, right? That is potential at the bulk phi, so that is also included here. Okay, so all these parameters are included in, that is the device parameters or process parameters are included in the MOSFET models. Yeah, so for example, model, you will what we call import this model library into your SPICE code by using this command dot model, name of the MOSFET, type of the MOSFET, level of the MOSFET, yeah, which level, and then the process parameter associated with the MOSFET. Even if you don't write all these process parameter, you simply write level 2. Level 2 process parameters will automatically selected by the tool. Okay. Similarly, for PMOS, you will again use the same word dot model PMOS. Okay. And then you have to define your current sources and voltage sources. So in the previous example, this example, that is, you have a I bias current source which is appearing between 1 and 0. Positive is 1, a positive terminal of this current source is 1 and negative terminal is 0. So current source I bias is between 1 and 0. So you declare it in your SPICE code file, that is I bias is existing between positive terminal 1 and between negative terminal 0, yeah, 1 and 0. And the value of that current source is 200 microampere. Similarly, VDD, that is voltage source, is appearing between 6 and 0. 6 is the positive terminal and 0 is ground. And the value of this is 5 volts. Similarly, positive and negative supply, that is V minus, V plus and V in is also existing. So depending upon in between which node it is connected, you have to write it here, right? And then assign the value, yeah, 5 volts or whatever, 2.5 volts or 0 volts, right? So then you will find U here corresponds to micro, right? So if I say I bias is a current source, so I write only U, so you will make the simulator understand that it is microampere. If I write N here, so that means nanoampere. If I write small m, so that means milliampere. If I write capital M, so that means mega, right? So all these values are considered by the simulator. Then for bringing in the MOSFETs, right? So we say that we have 4 MOSFETs over there, right? So 4 MOSFETs are there. Okay. Let us say, let's talk about this MOSFET. So, the gate is 3, right? This is drain, and this is gate, and this is source, right? So the drain is at 5, gate is at 3, and source is at 1. Okay. So drain, gate, source, bulk. Yeah? So we have to mention whenever we write the, which MOSFET we are using, the MOSFET model. So we say that M starts with, MOSFET, if you want to, bring in the MOSFET from the library, so you will bring it using this command, that is M, capital M stands for MOSFET. So this is again a reserved keyword. And 1, 2, 3, so these you can write depending upon, this can be anything, either they can also be A, B, C, D. So M1 is MOSFET number 1. So that is connected between these 4 terminals. Yeah, MOSFET is a 4-terminal device. Okay. So if I take NMOS, so source and bulk are tied always. Yeah. And these terminals are drain, gate, source, bulk. Okay. So this is 5 is the drain of the M1, 3 is gate, 1 is source, and 0 is bulk. Okay. Source and bulk are always shorted in a MOSFET, N MOSFET. For PMOS, you short source and bulk. So for example, here PMOS is in between 5, 5, 6, 6. Yeah, that is between drain, gate, source, bulk. Okay. So this is how you represent your MOSFET in your SPICE file. So let's say M3 5566. Let us go back here to this circuit. So this is M3 is PMOS between 5 drain. Where is drain here? Drain is here. 5 gate is again 5. Source is 6 and bulk is also 6. Yeah? That is M3 is this transistor. Okay. which is connected between drain gate source bulk, that is 5566. Yeah, source and bulk are shorted. Bulk is maybe here, so bulk is shorted. Yeah, 5566. So this is M3. So you'll have to also mark out the number, that is, this is M1, this is M2, this is M3, this is M4, and depending upon the drain gate source bulk nodes, you'll have to write here, right? So you write all those 4 MOSFETs and then write the type of the MOSFET, not the type, the name of the MOSFET. So the same name, you write NMOS here, or maybe anything. You can even write your name here, but the same name will appear in the when you are importing the model. So here you will write the same name, whether it is you have used NMOS or maybe A, B, C, D, or maybe your name. So you will write here. Then this is the type of the MOSFET. So this is
the code are for which software, sir?
For any software, for any SPICE level software, you will use the same thing, same SPICE code. The technique for writing the SPICE code is same for all softwares.
But sir, in LT Spice, the inbuilt is there. Like
yeah, so that is what I'm saying. So inbuilt is there. So if you want to modify these parameters, so inbuilt you give some parameter, you decide the width or length of the MOSFET, okay, and you will finally import this kind of CMOS file if you want to incorporate or make changes to any of these parameters. Maybe you want to make changes to let's say width or length. There also in the schematic also you can make changes, and the other way is to make change here, right? So similarly, load capacitance also you can change either here or in the schematic. Okay. Similarly, the model, the process parameters. So the process parameters, if you are not able to change there, so you can change the process parameters here in the code file, right? So it is good to know how to write the code rather than letting the tool do everything for you. It is good to know how the tool code is written. Yeah? This is more powerful measure of doing simulations. Yeah? You can make changes here easily. Any process parameter you want to change, you can directly change here, either than going back to the level 2 model files which are existing in the tool. Maybe the tool doesn't let you to change any of these model parameters. So model parameters can also be changed. In fact, you can create your own model models to run simulations, right? So maybe if I say that, maybe let's say I want the gate to bulk, or maybe let's say I say that oxide thickness should be, let's say 10 nanoampere. Okay, so that you can directly change here 10 nanoampere instead of changing the model library files in the tool. And maybe if the tool doesn't permit you to change, then you will never be able to change this oxide thickness. Yeah? So it is good to know how to write the code, because this is more powerful measure of doing simulations, right?
Okay, sir. Thank you.
Right.
So time ho gaya sir.
Okay, so maybe I'll stop here, and then we'll meet in the next class tomorrow. Not day after tomorrow, I think we have a class.
Yes,
Then,
sir. Yes, sir.
Yeah. So the meeting is ended.
Sir,
Yeah, please.
sir, when we will perform our assignments, then should we use any capacitance at the output of our inverter?
So I think already mentioned that you have to use 100 femtofarad.
No, yes, sir. But you told them that already in our SPICE model there was inbuilt capacitance.
Yeah, I'm not sure whether it is there or not, or what value they are using. They are using some other value, or maybe it is not existing there at all. So, but yes,
Okay,
I want to incorporate this. So,
Okay.
Yeah.
Okay, sir. Okay. Thank you.
So if you have any other question, then please you can ask, or otherwise the class is ended.